Okay, hello everyone. Good afternoon. And today I'd like to talk about our RL-based control framework for batteries to do arbitrage in imbalance market. So first, let's talk about briefly imbalance settlement mechanism. So as you know, there is a need for keep the balance in the grid between supply and demand, and this is the responsibility of TSOs. And they basically do that to make sure there is always frequency is always maintained in an acceptable range. And to do that, they try to penalize deviated participants who basically deviate from their own nomination by imbalance prices. So as an example, I just want to show you a day of imbalance prices in Belgium. So as you can see, first of all, imbalance price is really highly volatile, and it changed basically from minus 600 to plus roughly 300. And also it changed a lot of time signs, and there's a lot of quick changes basically between the positive and negative signs there. But this trend will become even worse because of a continuous rise in the penetration of renewable energy resources. And as you know, renewable energy resources add more uncertainty to the generation. And because of that, BRPs will face even more difficulty for balance their own portfolio. And as a result, imbalance price will become even more increase more than this event. And I also like to grab your attention to the imbalance price trend of Belgium as well. So as you can see, there is a both increase in the median and also volatility of the price when we look at the recent years, especially. But actually, this volatility is not that bad because it provides some opportunity for participants to do arbitrage in this market and basically charge the battery when the price is low and discharge the battery when price is at high value. But it's not that easy to do this arbitrage. And there are some challenges basically to participate in imbalance market. The first and most important one is that imbalance prices are highly uncertain and highly volatile. We don't know even what's the current imbalance price for the current quarter hour, and it will be calculated when the quarter hour is over, basically. And the next thing is that the settlement happens every quarter hour. So our BRPs needs to always keep the eyes on the imbalance price and current situation of the market and quickly change their action basically every minute or every 2 minutes, and basically in a minute level base to make sure that they are basically in the right direction of the market and making money out of it and help the grid as well. So to deal with these challenges, we try to propose distributional RL-based control framework for the batteries to do arbitrage in imbalance settlement mechanism. Generally, we focus on RL because, first of all, they are faster in inference time compared to model-based optimization problem methods, where they need to solve the optimization problem and it takes time normally. And also, we can deal with stochasticity and nonlinearity in our environment by using RL. But as you probably know, the main challenge of using RL is that they are not really safe to use, and there is no guarantee basically for safety of policy, RL policy. So for solve this problem, we try to propose a policy correction framework, which is basically an extension of knowledge distillation process, standard knowledge distillation process. And we try to correct and constrain our policy using differentiable optimization layer. So since our problem is a sequential decision-making problem, we formulated the problem as an MDP. So in the formulated MDP, we have an environment, which is basically our battery and power grid. We have our agent, which is our decision maker. In our case, as I mentioned before, we use distributional RL. And the main idea of distributional RL is just basically estimating the distribution of returns instead of estimating a single value, which is the expected value for the cumulative reward. And at each time step, our agent can see some information, which we call state. The state in our problem includes some time-related information, such as, for example, minute of quarter hour, and also some characteristics of the battery, like SOC, and also indicative tolerance price, which is a minute-based price published by Elia, which is a Belgian TSO. And based on this state, our agent tries to take an action, which can be either charge or discharge the battery or do nothing. And after taking action, the environment provides a reward, which is in our case, energy cost. So let's quickly have a look at RL methods. So we use DQN and DDQN methods. DDQN is a distributional version of DQN. And the main idea of DQN is just learning Q values, which is a cumulative future reward for the current state of the environment. And we use Bellman equation to estimate the Q values. And after that, we try to take an action in a way that to maximize the Q values. And in the distributional DQN, we replace this Q network with Z function, which is basically probability distribution of returns. And it leads to the equations that you can see in the slides. But as I mentioned earlier, there is no any guarantee for RL methods to basically lead to a safe policy. The main reason is that there is still they are data-driven method, and there is black box neural network that we don't know what's exactly happening inside it, and we don't know, we are not sure exactly why this action is taken, basically. So the goal is to avoid non-intuitive or catastrophic actions. If I want to give an example of catastrophic action or non-intuitive action is, if I'm back to my first slide, for example, the price that you can see, minus 600, we know that for sure this is really low prices. And if we take a discharge action there, it means that we are doing something at least from human perspective, non-intuitive. Because as a human, we know, for example, imbalance market prices should be between, for example, 2000 and minus 2000. So to deal with that problem, we try to use the knowledge distillation. So we extend the standard knowledge distillation process, as you can see in this slide. So basically, in knowledge distillation, we have a teacher model, which in our case is a pre-trained RL model that we have used. And also we have a student model, which tries to mimic basically the teacher model. And in our case, we try to constrain or correct our policy while the teacher model is transferring its knowledge to student model. So, so as you can see in the slide, optimization layer is a key part or key novelty of our extended knowledge distillation process that we have. And if I want to be focused on this differentiable optimization layer, first, we need to define what's exactly the human intuitive property for a policy. So we came up with these three properties for that. So first one is obviously charging at very low prices. Second one is discharging at very high prices. And the last one is the policy should be monotonic with respect to price and SOC. So basically, if I want to elaborate a bit more this property, it means that if we are in a specific SOC, for a specific SOC, if we take action charge for a given price, we should also take action charge for prices below these given prices. And we formulated these three properties as a convex optimization problem, and basically enforce these three properties via our differentiable optimization layer. So let's move on to our results. So first, I'd like to talk about our simulation results. So as I mentioned before, we used DQN and DDQN as our RL methods. Our battery that we have used was 4 megawatt, 8 megawatt hours with efficiency of 0.9. We used Belgian imbalance price of 2023 for training our model. And decision making time resolution was 2 minutes, and we train our model for 50K episodes. So in this slide, you can see our learn policy for the DDQN before applying policy correction. So as an example, I took two time basically, and plot our policy heat map. So in this policy heat map, the x-axis shows the imbalance price, and y-axis shows the SOC. And as you can see at the first glance, it's easy for us as a human to see it's really non-intuitive policy, at least. But after policy correction, you can see that this policy turns to these two heat maps, which means basically they are smooth and at least from human perspective, intuitive. And if I want to be a bit more specific, so this region that I highlighted was basically corrected based on our first property, was which basically pointed to charging at very low prices. This part of the region was corrected based on the property 2, which was the discharging, and this blue hole in the middle of the policy was corrected based on the monotonicity constraint or property that we had. And so we have everything ready. We have our safe RL policy that we can implement basically on the real world, or at least we can trust it. So we tried that actually, and we implemented our policy on a real world battery, which was installed in home lab. And for that, we use our home lab gym, which is a real world testbed, and we try it. And in this slide, you can see our results. As you can see in the bottom figure, there is no any basically, if you compare with the first figure, which is the imbalance prices, you can see prices are, at least actions are intuitive, and there is no any non-intuitive action in that size. But of course, we had some differences between the simulation and our experimental results. And these differences are mainly because of battery hardware latency, which was 10 seconds, and also pricing community failure, which we faced because India had some technical issues, and basically we couldn't get any imbalance signal for a half a day. And also the last one, which is we model the efficiency of the battery linear. So if I want to wrap up our presentation, so as I talked about it, we propose a RL-based control framework, which could outperform the rule-based controller by 36%. And also we try to correct our policies using a post-processing step, and we try to enforce some human intuitive properties using differentiable optimization layer. And finally, we successfully deployed our model on the home lab battery. So that's my first slide. Thank you for your attention. If there's any question, I'd like to answer.